Okay, hello everybody. I hope everyone is having a good weekend. This is the pre-calculus review video um, for our test that is Monday, and it is over rational functions. I'm just going to pretty much do one or two of each problem within each section of the review, just to kind of walk you through it, and then you do one on your own. Um, and yeah, so I'm going to be cringy, but please like and subscribe to my YouTube channel because I want to be famous one day. Let's get started. So with this first one, it's just asking to find the domain. And remember, domain is all possible x values. And in our case with rational functions, the thing that we can never do is never divide by 0 because we would break math and make Miss Hester sad, which is bad. So our goal here to find our domain is to figure out wherever our denominator would be 0. So what we'll do is we'll have x squared minus x minus 6 equal to 0 because we don't want that to happen. So we don't want it to be equal to 0. And that'll help us find our domain. So from there, this is a quadratic function. So what I'm going to do, I'm going to factor it. And our method of factoring usually is big X. So I'm going to big X that. On top will be -6, -1. Multiply to -6, add to -1, -3, +2. So our new bottom will be x minus 3 x plus 2 cannot equal 0. So that means x cannot be +3 and x cannot be -2. And that's it for our domain. We can be everywhere except for those two places because that's where we would end up having vertical asymptotes, which we're about to get into momentarily. Okay. And you would do pretty much the same process on number 2. You would figure out where that bottom part would be 0, and that would be what your domain would not be. Okay, so now let's kind of expand on the idea of vertical asymptotes, but we're also going to add on those horizontal and slant asymptotes. So we're going to start with vertical asymptotes. And again, those happen when the denominator is 0. Okay, so very similar quadratic function on this next one. So I'm going to choose a different problem. Let's do number 6. So number 6, I want to figure out what my vertical asymptote is. And so I'm going to look at where my denominator is 0. So I'm going to do that pretty much the same process that I did when I was finding my domain. But I'm going to change my answer just slightly. So I have x squared minus 2x minus 3 equals 0 because this time my vertical asymptote is wherever my denominator does equal 0. So I want to be equal to 0 here. And then I'm going to factor that. So I'm going to use my big X method that I usually use, -3, -2. Multiply to -3, add to -2, -3, +1. So then my quadratic becomes x minus 3 multiplied by x plus 1. So that means my vertical asymptotes will happen at x equals +3 and x equals -1. And we have to have that x equals part because a vertical asymptote at the end of the day is a vertical line. And the equation for a vertical line is x equals and whatever that number is. So those are our two vertical asymptotes. Okay, great. So now let's figure out horizontal asymptotes. So horizontal asymptotes, we have been using that Bobo Botten eats DC. So Bobo was big on bottom, y equals 0. Botten was big on top, none. And then eats DC is exponents are the same, divide coefficients. So we're just looking at the exponents on the top and the bottom of our rational function in this case. Okay, so over here, we look and see that our exponent on top is 2 and our exponent on the bottom is also 2. So we are part of the eats DC portion of our horizontal asymptote. So there's that. And so our exponents are the same. So we're going to divide the coefficients. And in our case, our two coefficients are 3, and then there's that imaginary 1. So our horizontal asymptote will occur at y is equal to 3/1, which simplifies just down to y equals 3. So that's where our horizontal asymptote. Now, when we deal with slant asymptotes, if we want to have a slant asymptote, we can't have a horizontal asymptote. Okay. And so in this case, we don't have a slant asymptote. But let's just say if we did have a slant asymptote, what would happen with a slant asymptote is that happens when it's a very special case. It doesn't happen very often. It is when the exponent on top is 1 larger than the exponent on bottom. So it's a very rare case where um, the exponent on top of our denominator or on top of our fraction is bigger than the one on the bottom, but it's only 1 larger. Okay, so it'd be like x cubed over x squared. That is when we would have some sort of a slant asymptote, or wherever we have 1 larger on top than we did on bottom. And we would end up using some sort of division, or we would divide the coefficients, and that would be whatever the slope of that line is. It would end up being a linear line of some sort. So again, very rare case, doesn't happen very often, but it does occur when our exponent on top is only 1 larger than the bottom. But if we had like x to the 5th over x, just x, that's not when we have a slant asymptote. It only happens when we're 1 larger on top. Okay. So that's how we do those. And you guys can pretty much figure out the rest from there. All right, let's move on to the next section. So it says solve the equation or inequality algebraically. Okay, the most important part with these types of equations is we must have some sort of a common denominator. Okay, when we're solving equations that deal with fractions, we have to have a common denominator. If we don't have that common denominator, it is very, very hard to solve the equation. Okay, we're gonna go ahead and let's do number 8. Number 8 looks fun. Okay, so we have to find a common denominator. And in this case, I noticed that all 3 of my denominators are very, very different. Okay, but when we're doing these types of things, what I usually want to do is I want to make sure that all of my denominators are as simple as possible. In this first case, we're good. I can't simplify that at all. Can't do that with the second one, but on my notice on the last one, I can simplify that a little bit. And it's very similar to the one that we did on a previous problem, but I'm going to go ahead and do it. So I'm going to simplify this just a tad to see if I can get some nice factors and see if I can get some common denominators in between all my fractions. So big X that, -6, -1. So we have -3, +2. Okay, so our first 2 fractions did not change. So we still have our x over x plus 2 and 5 over x minus 3 is equal to, and then we have 25 now over the x minus 3 and the x plus 2 that we were able to factor that into. And what I notice is, hey, that's a really, really nice denominator right here, because I notice that this piece, the x minus 3, is also under my 5, and that the x plus 2 is also under my x. So what I can say is, hey, I've got pieces of that last denominator in my other 2 fractions. So then I can say that my common denominator here is that x minus 3, x plus 2. Okay, and what I'm going to do from here, I want to get those other fractions to have that common denominator on the bottom. So I'm going to multiply them by whatever piece they're missing in this case. So x plus 2 is already under my x, so I'm going to multiply it by that x minus 3 because that's what I'm missing. So then we'll have x times that x minus 3 all over x plus 2, which is what we started with, multiplied by that x minus 3 to get that common denominator on the bottom. Okay, good. Do the same thing on the 5, but now I already have that x minus 3 on the bottom. I want to add on that x plus 2. So I have that x minus 3 on the bottom that I started with. I want to add on that x plus 2 because that's what I need. I'm going to multiply that top by the x plus 2 as well, because whatever I do to the bottom, I must also do the top. Now, I notice the 25 already has both pieces, so I don't have to do nothing to it. It already has the common denominator that I wanted. I'm done with the 25. I don't have to do anything to it. I don't have to change it, don't have to multiply it. I don't have to do any additional work. Okay, so what I notice is this equation has an equal sign in it. And I notice that now all of my denominators are the same. What I can do now, if all my denominators are the same, I don't really care about them anymore, because to be able to solve the equation, I have to get my numerators to be the same. So I'm just going to kind of ignore the denominators now. So I'm going to get rid of them. So I'm just going to have x times x minus 3 plus 5 times x plus 2 is equal to 25. This is my new equation. It's without fractions. Yay, that's great. Apparently y'all are scared of fractions. I love fractions, but let's do less work and work without fractions for now. Okay, so from here, I'm going to simplify just a little bit to see if I get a nice function that I can either factor, simplify, and get x by itself. Okay, so I'm going to distribute that first x in. So I have x squared minus 3x distribute the 5, so I have 5x plus 10, and I'm equal to 25. Combining like terms, I have x squared plus 2x plus 10 is equal to 25. Okay, now I see a quadratic equation, which is great. I know I'm going to end up factoring it with either big X or whatever method you prefer. But to be able to solve a quadratic equation, I must have it equal to 0 first. So I'm going to move that 25 over just real quick. So then I have x squared plus 2x minus 15 is equal to 0. Okay, so now I'm going to factor that because I'm at the end of the day, we're doing all of this work to try and get x equals some sort of a number. Okay, so I'm going to have negative 15 on top, positive 2 on bottom. So then I will have positive 5, negative 3. Okay, so my two factors end up being x plus 5, x minus 3. So I have a possibility of x is equal to negative 5 and x is equal to positive 3. Now, when I am solving rational expressions, I must check for extraneous solutions. So we must, that's terrible curly brace. Doo-doo-doo. There we go. Must check. Okay, I have to check my answers because we have that possibility of dividing by 0, which is very, very bad. So I'm going to check both of them to see if I get any division by 0. So I'm going to plug in, and I'm going to try negative 5 first. So I have negative 5 divided by negative 5 plus 2 plus 5 over negative 5 minus 3 equals 25 over negative 5 minus 3 and negative 5 plus 2. I'm running out of space, but that's okay. There we go. Okay, so if I notice here, if I were to combine all of these things down the bottom, I would never end up with having division by 0. So negative 5 is good to go. So that one's good. Yay. Okay, so now let's try the 3. Okay, so we have negative 3 over negative 3 plus 2 plus 5 over negative 3. Oh, I'm sorry, that should be a positive 3. That's my bad. Positive 3 minus 3 equals 25 over positive 3 minus 3 over 3 plus 2. Okay, so I notice I have a possibility of division by 0 in two spots. I've gotten 3 minus 3, which gives me 0, which is horrible. Ew. No, I don't want to divide by 0. So just because even that one spot I have division by 0 is bad. Okay, but I also noticed in that the second spot as well, which means I also have division by 0. So negative or positive 3, don't know why I keep saying it's negative, does not work. So positive 3 in this case is that extraneous solution. We didn't do anything wrong to find that positive 3 is a solution. We did all of our algebra right and all of our solving correctly, but unfortunately, when we plugged it back in, we got division by 0, which is very bad. So negative 5 worked, which is great, but 3 did not. So at the end of solving rational equations, we always have to check our answers because there's always a possibility of having that division by 0, which is not good. Okay, and you did pretty much the same thing on the 7, 9, and 10. Okay, so now let's talk about inequalities. This is the most recent stuff that we have talked about. And with inequalities, we use something called a sign chart. So the sign chart is the most recent thing we've talked about. Now, what I like to do is I like to think about this top line as a number line, and I use my special points or my special numbers. In this case, my special numbers, I'm going to look at the places where I have either possibility of division by 0 or I have an x-intercept or something like that, because that'll tell me where I'm going to be above or below the x-axis. So x minus 3 equals 0 tells me x is possible equal to 3. So I'm going to put a 3 somewhere on my little number line. And I'm going to do the same thing on the bottom. So I have x plus 1 is equal to 0. Oop, sorry. There we go, equals 0. So then I have x equals negative 1. Sorry, my dog is trying to climb all over me and get snuggles. We have x equals negative 1. So negative 1 is another spot on my little number line. Okay, now what I'm going to do is I'm going to check it at both of those little places because I want to see where we will have a positive or negative on the top or the bottom, because that'll tell me what I'm going to be, if I'm going to be above or below the x-axis. And I'm going to have a total down here, which I'll explain here in just a second. I'm going to draw a little lines here to make sure I don't get disorganized. All right, so again, I think about this top line as a number line. So I'm going to look at, let's say, a number. I'm going to look at a number that's to the left of -1 or that is less than -1. In this case, I'm just going to choose, I don't know, -2 because that works. So if I plug in -2 into -2 minus 3, -2 minus 3 will remain a negative number. It'll actually get more negative. That ends up being -5. And then we have -2 plus 1. That'll still remain negative. So I have a negative on both of those. But if I were to plug those back into my equation here, I have a negative divided by that negative, which ends up being a positive. Okay, so in anywhere to the left of -1 on my graph, I will be above the x-axis. So I will be above the x-axis is what I want to mark there. Okay, and I do the very similar process in between -1 and 3. An easy number there is 0, and I like using 0 because 0 makes my life easy. So 0 minus 3 will end up being negative. 0 plus 1 is positive. Now I'm going to do the same process I did here. I'm going to have a negative divided by a positive will remain negative. So this will be below the x-axis from between -1 and 3. Okay, I'm going to do a very similar process again. The number greater than 3 is 4. 4 minus 3 is actually a positive number, which is good. 4 plus 1 is also positive. So a positive divided by a positive will also be positive. So I will also be above the x-axis here. Now, back to our original question. So our original question asks us, where is this rational function going to be greater than 0? So when I'm greater than 0, I'm positive. Okay, so I have to figure out where I am above the x-axis, and I read that as an interval. So I have two places where I'm above the x-axis. I have here to the left of -1 and everything to the right of 3. So what those will look like as intervals, I will have from -infinity to -1, and I'm going to use a parentheses here because I do not want to be equal to 0. It just says strictly greater than, so I'm going to use parentheses instead of brackets here, but also that -1 is a vertical asymptote, so it can never equal -1 anyway. So from -1 to -infinity, I am greater than 0. So because I'm above the x-axis as we see from our sign chart. And then from 3 to infinity, we were also above the x-axis. Sorry, I forgot to close that. Now, just a kind of special thing about 3, 3 would be our x-intercept. Is so we would end up, if we did have a line underneath that 0, or underneath that inequality sign, I'm sorry, that would be a bracket if we had that line, but we don't. So I just kind of want to make a note there. That's an x-intercept, and this is a vertical asymptote. So I'm just going to do a VA. Um, so that's how we kind of deal with inequalities. We deal with that sign chart. And again, we think about this top line as a number line, and we go to the left or right of numbers to figure out what the values are. And then we kind of, depending on the problem, we divide or multiply our positives and negatives to see what we get. And then we go back to the original problem and we figure out which one we're actually looking for. Okay, so that's how inequalities will work. All right, so now let's go into graphing. So graphing without a calculator with rational functions is a process. Okay, and what I prefer to use is the Rady method or the Ratty method, whichever way you pronounce it. It just kind of is a little acronym that tells you everything you need to do in an order that you could do it. You don't have to do it in exactly this order. I just prefer to do this in this order to make sure I don't forget anything. Now, the only excuse me, the only word that isn't included in the rating method is the word holes. And holes is whenever we have a cancellation on the top and the bottom. And those are little spots where we don't have either a vertical asymptote or anything like that. It's just a space on the graph that is just a hole. We can't ever be there. Okay, but we always check for it. Okay, and then we have roots, vertical asymptotes specifically, tangency and togetherness, which we'll talk about when we get there, and behavior, which talks about horizontal asymptotes, and then we have y-intercepts. Okay, so I'm going to do number 16. Now, our first step when we're trying to use the rating method is we have to simplify first. Okay, because it makes our life easier when we're trying to find all of these pieces of our graph, like our vertical, horizontal asymptotes, all that good stuff. We want to simplify first. So I'm going to simplify the top a little bit because I see an x squared up there, but I also notice that I have a GCF of 2x up there because I have a common 2 that I can divide both of those numbers by, and there's an x attached to both of those terms. So I'll have 2x, and I'm left with 2x plus 1. Okay, so that's my new top. On the bottom, excuse me, I'm going to use the big X method, this is actually very similar to one that we did earlier. If not, I think it's actually the exact same one, maybe a little different. I don't know. So then we have, I'm going to big X that. So I have -15, -2, so -5, +3. So then I have X minus 5, X plus 3 on the bottom. Now, when I check for holes, I want to see the same set of parentheses on top, and I don't see that for either of those cases. So in my case here, I don't have any holes. So I say none. Now, roots. How we find our roots. Our roots, again, if you forgot, are our x-intercepts. And that is when our graph would equal 0. So I'm going to set my numerator equal to 0. So then I have 2x times 2x plus 1 equals 0. So then if I were to solve that out, I'd have 2x equals 0 and 2x plus 1 equals 0. Now, the reason why I have those two pieces equal to 0 is because I want to see where I can turn this equation, this whole entire thing, into 0. And I notice that I'm multiplying these two pieces together. And if I remember correctly, 0 multiplied by anything is 0. So I have to figure out if I plug in 0 here, I can make this entire thing 0, which is what I want because that's where I want to figure out where my x-intercepts is. So I take each piece since they're multiplying together and figure out where they're 0 because that would turn the whole equation into a 0. Okay, so then I solve. X is 0 here, and x would equal -1/2. So my two roots will be at 0, 0, which is the origin, and then we'll have -1/2, comma 0. And as I find things here, I'm just going to go ahead and graph them just to make sure I don't forget about them. So there's our first 0, and then I'm going to count these by half, or I'm going to do 2 blocks as 1. So I'm just going to kind of mark that. So this is a 1, that's, oh, -1, I'm sorry. This is -2, -3, and so on, so on. I just want to make sure that y'all know what I'm doing. So then -1/2, 0, which would be over here. So these are my two x-intercepts. All right, so now let's talk about our vertical asymptotes. So vertical asymptotes, I'm going to set my denominator equal to 0 because we found these earlier. So I'm going to I have x minus 5 equals 0, x plus 3 equals 0. So then my two vertical asymptotes are at x equals 5, x equals -3. And I'm just going to go ahead and draw those in. So here is my first one. And then I'm going to do it at the very end of the graph because I'm going by twos here. So there's my other one. So I might go off the graph just a little bit here today, but that's all right. Now, tangency and togetherness. I don't think I'm going to have either of those here. I'm going to explain why here in just a second. So tangency is when I have an some sort of an x squared term that's in parentheses on the top, say over x plus 2, just for funsies. And since I do not have this kind of squared set of parentheses on top, I do not have tangency. But if I did, what that would look like is at some sort of a vertical or some sort of our x-intercept. So at in this case 1, we would have some sort of a bounce behavior. It can be going up or it could be going down, either one. So that's what tangency looks like, just to kind of review that. And then togetherness is the opposite. So we'd have x plus 2 over x minus 1 squared. So we have this squared term down on the bottom. But what togetherness talks about is it talks about at a vertical asymptote, both sides of our graph would be going in the same direction. So we'd have something like that. And that's what togetherness means. The two sides of our graphs are coming together at our vertical asymptote. That's how I like to think about it. But if I look at our equation up here, we don't have either of those things happening. We don't have a square up here. We don't have a square down here either. So we don't have neither of those. Those don't happen very often, but when they do, we do have to look for them. So in this case, we don't have either tangency or togetherness. All right, so now let's talk about end behavior. So end behavior, as we said earlier when we talked about horizontal asymptotes, that uses the Bobo-Botten Eats DC. Do, 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 do. And in our case, I want to look at the original because the original equation, the unsimplified equation, is the easiest to look at for the end behavior, in my opinion, because it's sometimes hard to see, or if you don't remember how to count exponents and figure out what the power is from the factored version of your equation, it's easier to look at the original equation to see what the power is on the top and the bottom. And what I notice is I have a power of 2 on top and a power of 2 on bottom. So I'm part of that eats DC part. So my horizontal asymptote will happen at y is equal to 4 over 1. So it'll be at 4. So there is my lovely, I'm going to make this thicker so I can see it. There we go. So there is that. And I'm going to do the same thing on my vertical asymptotes real quick. Do, 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 do. There we go. So there is my horizontal asymptote, which is at y equals 4 over 1. And then last but not least, I have my y-intercept. And for my y-intercept, I just set x equal to 0 and solve. Now, what I also notice is that I already have a y-intercept at the origin when I found that root. But just to kind of go over it real quick to make sure everyone knows what I'm talking about, we'll have our 2 times 0 times 2 times 0 plus 1 all over 0 minus 5 over 0 plus 3. Simplify just a little bit. This whole top becomes 0, and that bottom turns into negative 15, but 0 divided by anything just gives me 0. So our y-intercept is indeed at 0. Okay, so now let's talk about how we figure out where our pieces of our graph are going. And this is kind of where we either use a sign chart or something like that. Uh, excuse me. So let's see. So our graph, what I can do is I can figure out which side of my horizontal asymptote my graph will be on is if I plug in a number real quick. So in this case, I'm just going to plug in a number that's to the left of -3, so that's -4 in this case, and I'm going to kind of use my sign chart real quick. So I have a couple of special points. I have one at -3, -1/2. I have one at 0 and one at 5. Okay, so if I were to plug in I have 2x, I have times 2x plus 1, and I have x minus 5, x plus 3. There we go. So if I were to plug in a number to the left of -3, I'd have a negative number here. And then 2 times negative number, or 2 times -4 in this case would be -8 plus 1 gives me -7. So that would be a negative times a negative, which gives me that positive. Okay. And then if I were to plug in a -4 into here, -4 minus 5 gives me -9. -4 plus 3 gives me also a negative number. So I have negative times negative, which is positive. So what that tells me is I'm going to be above the x-axis, and I have to be then above my horizontal asymptote. So I'm going to have my upper, or this part of my graph up here, and that's just kind of using my sign chart to help me out. Okay, now since I do not have togetherness at my vertical asymptote or at any of my vertical asymptotes, I must be going the opposite direction for this side. So I'm just gonna, I want to make sure that I pass through my 2 x-intercepts. So I'm just gonna do that real quick. And I'm just gonna go in that direction. And what I also know is that I do not have any tangency, so I have no bounces here. So I know I'm going to go through both of those. This is going to look really weird, but that's my graph. I'm going to be going in the opposite direction here, and I'm also going to be going down on that side, which means I'm going to be going, if I were to continue off this graph, it would be up here. Okay. But the important part that I care about is like the most amount of points on your test will be from this. So if you can get all of this and just kind of sketch the graph, I'm great with that. This is a terrible sketch because Miss Hester can't draw, but this is what I care about. I would love it if y'all were all able to, get this part of a problem on the test. But that's how you use the Rady method to graph rational functions. I hope this review video helped. If y'all have any questions, we'll go over them day of before the test. Again, please like and subscribe to my YouTube channel because I want to be famous. Oh no, perfect timing. Okay, have a good night, you guys. Bye bye.